Welcome to section 9.4. We are doing the only section in pre-calc where we're doing proofs. And we told you this one was coming, and so here it is. It's called math induction. One thing I love about this section, besides the fact that it's a proof, is that there is always one specific way to set up your proof, and you follow that proof every single time you do it. And so that's really nice. Now I am going to be a stickler on certain things though, so be aware of that. Please pay attention to wording that I'm asking you to use, and also setup, okay? So let's look at our first one. Consider the following sequence. As I look at this, is it arithmetic or is it geometric? Well, if I look, how do I get from 1 to 3? I add 2. To get from 3 to 5, I add 2. To get from 5 to 7, I add 2. So therefore, it's arithmetic. Okay, it's arithmetic because our difference is 2. Okay, or basically we're adding 2 each time. Now, find a formula for the nth term, and we're going to ask you to simplify it. Okay, so if I write my first term, we start with 1, and we add 2 for every next term after that. Now, I'm going to distribute this, and if I do, I get 2n minus 2. So my nth term, 1 minus 2 is negative 1. Plus 2n. Let me just make sure there's some space in the middle here. It's negative 1 plus 2n. The reason we want you to write it this way, and you've probably already started writing it that way after looking at the answers in the back of the book, is this is going to help us simplify what we're doing. Now, in order to find the first 5 partial sums, let's go back and discuss this. The first sum means just take the first number, so I get a 1. The second sum means add the first 2 numbers, so 1 plus 3 is 4. The third partial sum means add 1 plus 3 plus 5, which is 9. The fourth partial sum means add the first 4 numbers, so 1 plus 3 plus 5 plus 7 gets you 16. And the fifth partial sum means add the first 5 numbers together, you get 25. Now, if I want to find the nth partial sum, we talked about how Gauss was able to get this in a few moments. Our formula is n over 2 times the first term plus the nth term. And my goal is to simplify this. Okay, now I'm going to use my nth term above. So here's how it works. I take n over 2, and I times it by the first term, which is 1, plus the nth term is a formula that you gave you. Negative 1 plus 2n. Okay, so I'm going to simplify. Negative 1 and a positive 1 cancel. So I have n over 2 times 2n. And if you look, the 2's cancel out, so I'm left with n squared. What we have just done is found a formula for the sum of any number of terms up to the nth term, which is 2n, negative 1 plus 2n, or I'm going to write it a little different, 2n minus 1. And we've said if I add up all of the terms from the first term to the nth term, the sum is n squared. So what I could do is say find the sum of the first 750 terms. It's way easier to plug 750 and square it than it is to do this sum and have to find the 750th term. Now, our goal in an induction proof is to show that it works for every value of n. The problem is because n is part of my formula, I have to pick another letter. Okay, pick another variable to use to show that it works for all of them. And so what I'm going to do, and your book does, is use the letter K. So the first thing we do is that it show it works for K. Actually, I'm going to call that number 2. Number 1 is show that it works for the first term. Then 2 is show that it works for K. And then 3, prove it works for k plus 1. This seems odd, I know, which is the next term. Okay, and so it's a 3-step process. Now, your book only describes it in 2 steps. I'm going to split it up into 3, truthfully, just like we did here. So prove the statement is true for the first possibility of n. Now, I'm going to say usually it's n equals 1, the first term. Every once in a while we say start at 3 or start at 5, so just kind of be aware of this. This is called the base case or step, and truthfully it doesn't matter to me. Okay, step 2, we're going to assume, see that word, underlined it, bolded, highlighted, that has to be part of your proof. We're going to assume that P of K works. I'll tell you what that means. And then here's where my step 3 is going to come in. From that, prove that K plus 1 also has to work. And this is called the inductive step. And my guess is I'm going to walk through it here, and we're going to walk through it again when we get in class. But this is the idea. It's a 3-step process, and I'm going to walk you through all 3 steps. Once you get the general idea, every proof follows this same setup, which is what I love, because I felt like in geometry you had to kind of guess your way through. There is no guessing in this case, which is what I like. All right, so here we go. Let's try it. What we're going to ask you to do, just to make sure that you understand what P of K plus 1 is we're going to ask you to kind of show me how that works, okay? So we give you that P of K is 1 plus 2 plus 3 all the way up to K, and we give you a formula for it. Okay, when we do P of K plus 1, the way it works is we do 1 plus 2 plus 3 all the way up to K, and you always start at K, and then go your next step, which is a K plus 1. So you're always going to go to the K that's there and just add in the extra term. And now every time I see a K here, I'm going to put in a K plus 1 times K plus 1 plus 1. So I replaced it here. And then all over 2. Now I don't like the look of this, so I'm going to simplify it. K plus 1 times K plus 2 all over 2. Okay, and right now I'm just trying to get you used to the idea of what is P of K plus 1. I'm going to show you that as we go. Let's try one more. P of K is the sum of 1 plus 3 plus 5 plus whatever. This is actually just what we did, that 2n minus 1. We just did it again. Now, to prove K plus 1, I'm going to start off the same way. 1 plus 3 plus 5 plus all the way to whatever was there, plus this 2K minus 1. But what I'm going to do is now add in another term, the K plus 1 term. Okay, so we're going to add the K plus 1 term into here. So plus, I'm going to go like this, 2 times K plus 1 minus 1 should equal. So this is the K term, this is the K plus 1 term. And then my sum, where I see the K, I'm going to put in a K plus 1, and I'm going to square it. I know this seems weird, so go with me. Okay? Now, the first one you're probably going to write, just flat out write down. The second one is when I want you to really start thinking, okay, what should come next? What do I start with? Things like that. Okay, so here we go. Now, I'm going to take you in the 3-step process. Okay? Now, as we go through, let me start from the beginning. We said step 1 was our base step. Okay? So I'm going to label these. I'm going to start and say when n equals 1, what I want to do is show that the sum is going to get you the same thing as when you use the left side and when you use what it equals. Okay, so the sum of 1, the first partial sum means just add up the first term, which is 1. If I use the formula and I want to show that that works, is it the same thing as when I get 1 squared? So you show it first by adding up your terms, and then second, go across the equals and plug it in. If you say yes, then we're good. So I'm just gonna, I'll come back and write some stuff in. Okay, the second thing, these words have to be there. We want to assume that P of K, I'm not going to use P, I'm going to use S. That the sum of K terms, and I'm just going to, you know what, I'm going to change my wording here. The sum is true. Because I want to assume it's true. So I'm assuming that S of K looks like this. And all I do is take S of N, and instead of N's, write K's. So 1 plus 3 plus 5 plus 7 plus all the way until you get 2K minus 1 will equal K squared. And I have to assume that this sum is going to equal to be K squared so that I can use it. My third idea is that I'm going to prove that S of K plus 1 equals, and all I'm going to use is only the sum. So I'm going to plug in, instead of N, I'm going to plug in a K plus 1, so that I have K plus 1 squared. My goal is to prove this, that by the time I'm done, I can get S, or K plus 1 squared. Okay, so here we go. In order to do this, we do exactly what we did before, and we find the sum of K plus 1. Okay, so here I go. This is the big step. S of K plus 1. What we do is start with what we have above the sum. 1 plus 3 plus 5 plus 7. And like we did above, we always go to the K term first. So like right here when we gave us the K term, so we go to the K term and we add in the K plus 1 term. So 2 times K plus 1 minus 1. Okay, so you go all the way to the K term. So basically you take this stuff right here and you just bring it down. And then you add the K plus 1 term. Now, because I took all of this and I moved it down, all of this we set above equals K squared. So all of this is K squared. And then I have this extra stuff. So if I distribute it, I get 2K plus 2 minus 1. I'm running out of room. K squared plus 2K plus 1. Well, if my goal, what was my goal? My goal was to get a K plus 1 squared. Well, if I look at this, I can factor this to be 1 and 1, K and K, and I end up getting K plus 1 quantity squared. And because I've shown that, we're done. You know me, smiley face at the end if we're done. Okay? So let me change my color. I'm going to walk through this again with you in terms of different words. So maybe wording-wise, you kind of see the process. So the first thing, we want to show both sides are equal when using the first term. Now, keep in mind, this said the first term is 1. Sometimes they'll tell you the first term is 3, which means you start by adding up 3 terms. Okay, so just be careful in that. Second thing, what we're going to do is we're going to assume S of K is true, and basically we're going to replace the original with K's. Okay? Third thing, we're going to prove what S of K should be. We got to show that this is what we're going to get. So I plug in the K plus 1 in for my N, and then what I'm going to do is I'm going to use the sum. I'm going to write out the K terms and add in the K plus 1 term. Okay, and then my goal is to basically get the same value, get the same expression as what I thought as what k plus 1 should be. Okay, so this is the overall idea. And again, I'm going to take it in the 3-step process, and hopefully we can get through this. So let's flip to the back. Let's try another one. Okay. Taking a look, we give you this. Now here's my starting point. This says start by using 3 terms. So when I do this, I'm going to say when n equals 3 this time, because I'm starting at 3, I want to start with the sum of the first 3 terms. So that means take 1 plus 2 plus 3. That's these first 3 terms. What I want to do is show that it equals when I plug a 3 into this side. So 1 plus 2 plus 3, 5 is 6. What I want to know is when I do 3 times 3 plus 1 all over 2, do I get 6? Well, 3 times 4 is 12. 12 divided by 2 equals 6. And because I can show it by adding up terms and then show it with the formula, the fact that I get 6 both ways means that I can move on. Now, if you can't do that, then there's no point in improving this. Okay? And I'm going to tell you right now, you'll always be able to make that work. So the first part is the sum and then the formula. Okay? And you want to show that both of them equal the same value. Okay, 2, you have to use the words assume that S of k is true. And we want to say what is S of k. S of k just means replace the original with k's instead of n's. Okay, so 1 plus 2 plus 3 plus all the way up to k should equal k times k plus 1 all over 2. Okay, third thing. We want to prove that S of k plus 1 should equal, now here we're only using the formula. Okay, I'm going to use the sum when I prove it. Right now I just want to figure out what I'm supposed to prove. So what I do is instead of n's, I put k plus 1. So k plus 1 times k plus 1, plus 1. Do that again. K plus 1 plus 1 all over 2, which is k plus 1 times k plus 2 all over 2. And this right here again is what my goal is when I end up. Okay? Now how do I do that? Well, now I'm going to use my sum. Once I figured out what formula I should end with, I'm going to use my sum. And my sum says, write the k sum, so 1 plus 2 plus 3 plus 4, all the way to k, and add in the k plus 1 term. Okay, now, all the way up to k is what we have above. And we said that was equal to k times k plus 1 all over 2. Now I have to add in a k plus 1. So this is the sum of k, and then I add the k plus 1 term to it. All right, now I need a common denominator. So I'm going to multiply this by 2 over 2. If I do that, I get k times k plus 1 over 2 plus 2 times k plus 1 over 2. All right, I'm going to do a little work a second. So I have k times k plus 1 plus 2 times k plus 1 all over 2. This is the idea of grouping. Okay, when we factor, they both have a k plus 1. So I can pull a k plus 1 out. The first term has a k left. The second term has a 2 left, and I can divide it all by 2. Since this is my goal, I'm done. Okay, so, boy, I love induction proofs. We told you there were, again, one section of proofs. If we can make it through this proof section, we're going to be okay. You'll notice, though, I'm always following the same process. And this may be something that we want to just sit down and do more and more and more proofs after school, and we can do that. But the idea is the same. I mean, we're following the same process all the way through. It's the process that's weird. Okay, so let me keep moving on from here. Those are the induction proofs. The rest of it, I'm just going to show you a brief example. And actually, this stuff should seem pretty familiar because we've done chapter 12. Okay, find a formula for the sum of the first n terms. Well, is it arithmetic or geometric? Well, I'm going down by 3 each time. So my first term is 25. My difference is -3. Because it's arithmetic, to find the sum of n terms, we take n over 2 times the first term, which is 25, plus the last term. Now, where's our problem? Well, shoot, we don't have the last term, right? Okay, so we're going to have to find that first. So I'm going to get my nth term, and I'm going to put that over here. In order to find the nth term, we said take 25 and subtract 3 for every next term. Now let's simplify by distributing the -3. So 25 minus 3n plus 3 is 28 minus 3n. This is what goes in my formula. So I have n over 2 times 25 plus 28 minus 3n. Let's simplify this a little bit. 25 and 28 makes 53 minus 3n. And if you want, you can kind of distribute this in. Actually, I do want you to distribute this in. So what I get is 53n over 2, because 53 and 2 can't reduce, minus I have 3n squared over 2. I know that doesn't seem any better, but I do want you to leave it here because some of the time we are going to be able to simplify a bit more. Okay? Now, if I wanted to find the sum, let me just extension this a minute. If I wanted to find the sum of 26 terms, I could take 53 times 26 and divide it by 2, minus 3 times 26 squared over 2, and I could get a 26 partial sum. And this is the idea. We can then say to you, okay, find 142 partial sums, or find whatever. This allows us then a formula to be able to do. Okay? Now, this is the idea of finding the sum of the nth partial term. You're going to have to do this as we go through. The last one I want to move up. Normally we do chapter 9 before we do chapter 12, but because we run out of time, we're going to deal with powers of integers. This actually should seem familiar because we used these sums in chapter 12, but let's give them to you anyways. The sum from 1 to n of an x. Okay, now different letters, instead of I, they use x, but same difference. If I do 1 plus 2 plus 3 plus 4, as we do this all the way to n, it's like the sum as I goes to 1 from n of I. It's n times n plus 1 all over 2. Okay? Second one, the sum from 1 to n of x squared, or I squared, is like saying 1 squared plus 2 squared plus 3 squared all the way up to n squared. What was the formula for our I squared? Well, it was n times n plus 1 times 2n plus 1 all over 6. Again, I hope these seem familiar to you. Let's do the cubed one, only they call it x instead of I cubed, but it's like saying 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. The cubed formula was n squared, n plus 1 quantity squared all over 4. All right, I'm going to go a little higher than maybe what chapter 12 did. Let's go to the 4th power. So 1 to the 4th plus 2 to the 4th plus 3 to the 4th all the way to n to the 4th. n plus 1 times 2n plus 1 times 3n squared. Let me erase that so you actually can read it. 3n squared plus 3n minus 1 all over 30. And last one, 5th power. From 1 to n of x to the 5th. So 1 to the 5th, 2 to the 5th, 3 to the 5th, all the way up to n to the 5th. N squared is part of the 4th power, or the cubed, times 2n squared plus 2n minus 1, all over 12. Okay, so what do we expect you know? Personally, I kind of think you should know 1, 2, and 3. Because 1, 2, and 3 we did in chapter 12, right? So overall, in my opinion, the squared, single, squared, and cubed, I think you should kind of know. 4 and 5, oh my gosh, I'm going to give to you because I don't remember them either. Let's see if I can make my pen. I will give you those two. But let's talk about how to use them, and I think you're probably good with this, but let's talk about how to use them. I use the x formula, and instead of n, I'm going to put 10 in, right? So 10 times 10 plus 1, all divided by 2. And I use it in the 4th power, 10 times 10 plus 1, times 2 times 10 plus 1, times 3 times 10 squared. This is crazy, right? Okay. Thankfully, this is all calculator based, because if it weren't, we would be in trouble, right? This gives you 55. This one gives you 25,333. So my total is 25,388. And again, the goal of these, for the most part, all they're going to have you do is actually use the formulas to find a specific sum. But I at least want you to know them kind of going through. Again, 1, 2, and 3, I expect you know we've used them before. 4 and 5, I'm giving you because I don't remember them either. So that's the end of section 9.4. Again, this is our proof section. My suggestion to you is maybe you try a proof before you come to class, and then I can actually help you kind of fix some things instead of getting them wrong on the quiz. So we'll spend some time in class, but that's the end of section 9.4.